Hi, this is Mrs. Doris, and this is Lesson 7-7 entitled Exponential Growth and Decay. And that is our objective today, is that you will model exponential growth and decay, and we'll use some real-life type problems. First of all, exponential growth can be modeled by the function y equals a times b to the power of x. You have already seen this in lesson 7-6 when we dealt with the problem on rabbits tripling. So here we go. A has to be greater than 0 and b has to be greater than 0 in exponential growth. Or I'm sorry, b has to be greater than 1, excuse me. The base b is what we call the growth factor. And the growth factor is equal to 1 plus the percent rate of change. Expressed as a decimal. The initial amount is represented by the A, and the number of time periods is represented by the X. So, looking at our figure here, A is the initial amount, and you may want to label this. Okay. B is called the growth factor, and it is always going to be greater than 1. All right. And our X is the number of time periods. Okay, problem 1. Suppose that in 1985 there were 285 cell subscribers in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? All right, well, taking a look at our equation, y is equal to a times b raised to the power of x. A is our initial amount, and our initial amount of subscribers is 285. Okay. Now, we're told that they're going to increase by 75%. 75% expressed as a decimal is 0.75. So remember, we have to take 1 plus, and I'll write this as 0.75, and then we're going to raise it to the power of x. And so in 1985 is our initial year, which would be year 0. We want to know how many there are in 1994. So how many years is 1994 after 1985? Well, just quick count. We have 1986 would be year 1, 87 year 2, 88 year 3, 89 year 4, 90 year 5, 91 year 6, and so forth, 92, 93, 94, you would end up with a power of 9. All right, so, and that we get from taking our 1985 and our 1994. And you could just subtract just as easily. 1994 minus 1985 would also give you 9 years. All right, so let's rewrite this. We have y equals 285. Putting our growth factor together, we have 1.75, and we're going to raise it to the 9th power. So grab your calculator, and once again, please try this to make sure that you get the same answer that I do. And if you don't, then we need to talk about why that is. All right, so we're going to take 1.75 and we're going to raise it to the 9th power. And that gives us y equals 43,870, and I get 1.986. So we're going to round that up since we can't have a fractional number of cell phone subscribers. They either do or they don't. We'll round that up to 2. So 43,872 cell phone subscribers. All right. Number 3. Let's talk about compound interest. In compound interest, and be aware, this is the type of interest if you have a savings account at a bank or a savings and loan. This is how they do it. Compound interest is when a bank pays interest on both the principal or the deposit that you have, the money that you've put into the bank. Okay, on both the principal and the interest already earned. Okay, and the formula for compound interest is A equals P times the quantity, R1 plus R divided by N, and the quantity is taken to the power of N times T. Now you'll see in the box I have described what each of these variables represents. A is the balance in the account. P is the principal, which is the initial deposit. R is the annual interest rate expressed as a decimal. N is the number of times interest is compounded per year, and T is the time in years. All right, so problem 2. And by the way, I am not going to require you to memorize this formula. This is one that on a test I will give to you. I do not expect you to remember it. Okay, suppose your parents deposited $2,000 in an account when you were born. The account earns 4.5% interest, compounded monthly. What will the account balance be in 18 years? All right, so this is an interesting problem, and it'll be interesting to see how much the balance in that account would be. All right, so let's write down our formula. We have A equals P times 1 plus R over N raised to the N times T power. All right, so here we go. The principal is $2,000. Okay. We have a growth factor of 1 plus the rate, the annual interest rate is 4.5. When we express that as a decimal, it'll be 45 hundredths. No, excuse me. Need another zero in there. 0.045 is 4.5% interest. We're going to divide that by the number of times that the interest is compounded each year, which is 12. It's monthly, and there's 12 months in a year. And then we're going to raise that to the power of the number of months times the number of years. And we have 18 years. All right, so here we go. Let's get your calculators handy, and we're going to do, because this is such a long expression, we're going to do little bits at a time. So I'm going to leave my 2,000 in right now. I am going to take 1, and I'm going to add to that 45 thousandths divided by 12, which is 1.00375. 1.00375 represents our growth factor, and the number of time periods, it's 18 years times 12 months for each year, which would be to the power of 216. All right, so we're ready to put this into our calculator now. We have 2,000 times 1.00375 raised to the 216th power. And what we have, $4,489. And looks like a penny. We'll go ahead and round it to the nearest penny. All right, so you can see that in 18 years at 4.5% interest, the money will have more than doubled. And of course, the more money that's deposited, the more money you earn. Number 5. Or excuse me, slide 5, I guess is what I meant to say. Exponential decay can be modeled by the function, and it's exactly the same. A times b to the x power, where a is greater than 0 and b is less than 1. All right, now it's also important to know that it has to be greater than 0. So b is going to be a number between 0 and 1. It can't be negative, so, but it is a fraction. All right, the base b is the decay factor. Which equals 1 minus the, let's say, percent rate of change. Expressed as a decimal. The initial amount is represented by the A, and the number of time periods is represented by the X. All right, problem 3 then is going to be modeling an exponential decay situation. The population of fish in a lake decreases 6% annually. If the initial population is 5,000 fish, how many fish are remaining in 10 years? All right, so let's take a look. We're going to start with our model, and our initial population is 5,000 fish. Okay, now it's decreasing by 6% annually, so Our decay factor is going to be 1 minus 0.06. That's expressing 6% as a decimal, and we want to take that away from 1, which would be represent 100% of the fish. And then we want to raise that to the power of 10, which shows the number of time periods. All right. Again, let's do this in a couple of steps. 1 minus 6 hundredths would be 94 hundredths, and raise that to the 10th power. So here we go. Using your calculator, we have 5,000 times 94 hundredths raised to the 10th power. All right, and again, we're going to have to round this off to the nearest fish. The fish is either alive or dead. So we have 2,693 fish remaining after 10 years. All right, conservation departments use this quite frequently to determine population of animals and fish and wildlife. So this is an example of a exponential decay model. As we work on problems in class, if you have any questions, please ask.